Thank you very much for the introduction, and welcome to our presentation with the name Building a Computer Vision Research Vehicle with ROS. This is the agenda. I will start with an introduction and a short history section, followed by the main parts, triggering a heterogeneous sensor setup and/or calibration solution for cameras. Later I will cover enhancements that we did, for example, at the ROS player and recorder, and the talk will close with some words about data handling and our personal lessons learned while working with ROS. A few words about ourselves. As you may know, Daimler is the corporate parent of Mercedes-Benz, and the work that I am presenting today is not done by me alone, but with my colleagues. We all started in the corporate research in team pattern recognition and cameras as PhDs, and our research topics are pedestrian intention recognition, driver observation, and traffic light recognition. That means we are all working with camera images mainly and have a second strong focus on machine learning, wherefore we need good data sets. For research, we choose ROS, and to show you how we build our computer vision-oriented research vehicles, I'm here today. I'd like to add some words about my personal backgrounds regarding ROS, because I started ROS using at the University of Hanover, where the mechatronics labs that days was an early adopter of the KUKA U-Bot that you can see here on the right, the orange thing. The U-Bot originally came with ROS Sea Turtle pre-installed, and when I started working with the U-Bot in 2011, it was just migrated to ROS Diamondback. We also founded a team for the then upcoming RoboCup League at work, and when I started working on traffic light detection at Daimler in 2013, most of my colleagues were either not using a framework or the established one used in automotive context. I also started with a plain OpenCV until I wanted to exchange my image loader with live images from a camera, and therefore used a framework as well. While doing so and wrapping my classes by framework filters, I started to miss the introspection capabilities of ROS and also especially the documentation from the ROS.org wiki. We are almost free at Daimler, as Daimler PhDs, we are almost free in which tools we use at Daimler, so I switched back to ROS, which was not pre-installed on a corporate workstations, and that resulted in a lot of tries building ROS from source. But in the end, I think it was worth the pain, and about a year later, my New York PhD colleagues also joined the ROS train. Our research has mainly autonomous driving in mind, so I thought a quick little history about Daimler's path on autonomous driving would be interesting. The Daimler corporate research is participating in public research projects since 30 years, and as far as I know, autonomous driving at Daimler started with research vehicle called Vita. That's the one in the left. And it was also called the video bus. It had analog cameras, Intel 8086 processors of that time, and an extra generator installed that was producing the electrical energy needed. The bus was equipped with a vision system for automated driving developed by the German military that had the leading solution that days. In the early 1990s, the Prometheus project, for the Prometheus project, 2 Mercedes-Benz S-classes were equipped with this kind of vision system. And what remarkable is the thing that these cars were used to show things like adaptive cruise control, automated lane keeping at up to 130 kilometers per hour, automated lane change as well. Prometheus was followed by a project called Promote Chauffeur, which was about electronical coupling of highways, of trucks on highways. In more recent days, we showed an autonomous drive called the Bertha route in 2013 on public roads in Germany with the car called S500 Intelligent Drive. And a year later, we also showed this drive in the USA, and we also brought it to the truck world and bus world. Okay, as mentioned, our talk covers about research vehicles, and here they are. Our team has currently 3 Mercedes-Benz S-Class vehicles, and another vehicle is a 2016 Mercedes-Benz B-Class electric drive used for another research project. And the 2 in the top are used for traffic light research. and have relatively simple setup using the vehicle sensor data obtained from CAN buses as well as prototypically stereo cameras, and the other two have more complex setups including lidars, high-end odometry sensors, or infrared cameras. The one in the left, bottom left for example, has 7 cameras as well as 3 lidar systems installed. So cars already come equipped with a lot of sensors, and these sensor readings are transferred using CAN buses. CAN buses has message descriptions which vary from car to car, so to get the readings from the bus, you need a specific decoder. On the other side, this CAN message description is at least available for us as OEMs, so we implemented a ROS message generator that can create .message files from such a CAN message description, and the normal ROS generate message magic is used to create the message for each ROS client library as CPP or Python. The message description is also used for our decoder node that reads the CAN bus messages, decodes them, and publishes them as strongly typed messages as we all know it or expect it from ROS topics. All right, second thing is the prototypical hardware that we added to the car, like cameras and lidars. Whenever you want to use data from multiple sensors in low-level sensor fusion, you need 2 things: timestamps and frame IDs. And with frame IDs, I mean a sensor-to-sensor transformation. Regarding time, we ideally want to capture the surrounding at the exact same moment in time, and this across all different sensors at best. And in this context, we may have a heterogeneous sensor setup consisting of different hardware drivers and node wrappers, different capture cycle rates, and inside the current car, we have the CAN buses as well, which transfer sensor readings that are not time-stamped. So the question is how to handle these constraints. The kind of normal solution is setting up sensors at defined cycle rates and use, for example, software triggering. The image on the left, or on the left of the slide, is shown how it could be like. We have 4 cameras here that are transferring data to the PC and the CAN bus reader, which is also transferring data. The problem is that we have normally no insight on the camera drivers, so we do not know internal latencies, and using software triggering, in the end, the images will most likely not be captured in the very same moment. Most industry-grade cameras include a hardware triggering capability that could also be used. So when using a trigger bus, as shown in black color here, for example, controlled by a microcontroller that is generating the trigger, or also a main camera that is used as master, we can make sure that all captures are done in the exact time moment, but we still don't know when it is. So whenever sensors do not know about reference time, we have a problem with timestamping. We can use the normal ROS time now on data arrival, but for several different nodes, this will result in different timestamps, as they are all different processes using ROS time now. So using a time synchronizer across ROS topics afterwards will be difficult. Another thing is that ROS time now is always not correct, as it refers to the data arrival time and not the data acquisition time. So in the end, we want to know the moment of triggering in the reference time. In our case, we migrated our Arduino triggering microcontroller to an STM32F4 based microcontroller, and for this kind of microcontroller, Bosch showed on ROSCon 2015 a ROS implementation, and this project used the lightweight Internet Protocol stack in conjunction with a self-written XML RPC server and a ROS UDP implementation to directly publish and subscribe ROS messages without the need of a host PC. We adapted this solution and added the precise time protocol to the project, which enables us to publish stamped trigger messages that use reference time as well. So next slide here, you can see the added internet connection in red from the host PC to the microcontroller that is used by the PTP time synchronization as well as the ROS UDP implementation. In this case, the host PC is the clock master, synchronizing the time to the microcontroller. The microcontroller is the trigger master and uses the time to send out ROS messages with a header that includes the timestamps when the when the triggering occurred. And this message is received by the camera nodes, or generally said by the sensor nodes, which then can use this timestamp for the data when they arrive. Well, we still have the unstamped canvas, but we can't do anything there. But we can go one step further and add Velodyne LiDARs to the scene. The Velodyne itself has a solution for timestamping using a GPS sensor and the PPS, pulse per second trigger system, in conjunction with an MIA string. And in our setup, we can use the GPS time as a reference time. The microcontroller then becomes the PTP master and transfers the time to the host, which all will be GPS time. And in the end, we have all sensors living in the exact time, same time reference. All right. Initially, I said the second big thing for us is sensor-to-sensor transformation. So the reason behind this is sensor orientation. Even small errors here can result in huge position errors when we measure distant objects. So good calibration is needed. For cameras, a starting point is the camera calibrator.py node, which internally uses OpenCV camera calibration. And it has an informative UI that teaches you where to do your chicken dance and where data is needed. But it also picks images from the running video, which can result in motion blur, for example. It also does not allow you to modify the collected checkerboard poses, so you have to restart from the beginning if you press calibrate and decide the calibration is not good enough. And it does not generate a sensor-to-car transformation at all. So our solution, or our requirements at first, from the calibration is we wanted to be able to do calibrations alone. We wanted to have an on-demand checkerboard detection. We wanted to have a live detection inspection, and we wanted to be able to remove poses or to add specific poses. And we came up with this solution, a Windows 10 tablet that we installed Ubuntu on, which is a way more complicated than it sounds, and a checkerboard directly glued on the backside. We implemented a calibration client-server system where we get a live image using the the tablet's Wi-Fi connection. The operator can trigger checkerboard detections when pressing a button on the touchscreen, and the result is then sent to results slots where they can be inspected. If we need a bigger trigger, a bigger checkerboard, for example, it's also possible to use a really big one and to place the tablet on the backside. It's just important that you are able to press the trigger button, because then you can do it on your own. From the ROS graph behind is looking like this. We have the camera publishing images. We already also have a total station that can measure the 3D distance from our checkerboard to the car frame, and our calibration solution consisting of a calibration server running inside the car and the GUI running on the tablet. The server subscribes the images, or the image or images in case of a stereo system, as well as the distance data NTF. To allow live image streaming to the tablet, the server scales the image a little bit down and also publishes only with 8-bit depth, while everything else is running with 16-bit pixel depth. And in case of a stereo camera, both images are transferred side by side as one image. The server also includes a number of services: the on-demand checkerboard detection trigger, the calibration trigger, as well as services for deletion and detection and load save functionalities. This way we can do the calibration the conventional way, but in more detail, as we can call calibrate multiple times and each time get projection errors for all single images. Okay, 3 very quick slides regarding ROS tool enhancements in general. A first example is time shift recording. When we started to record traffic lights in urban environment, we wanted to capture the traffic light approaching. And in case of a halt in front of a red traffic light, we wanted to skip the red phase where the whole scene is more or less static. But we wanted to capture the moment the traffic light switches its color state. So we need to pause recording when the car stops, but we need to resume before we see the change in the state. Our solution was to modify the back recorder, that it continuously records into a RAM buffer and exposes a recording trigger topic. The operator can then request a start recording to some time in the background, in the past, sorry. And as long as this past data is still available inside the potentially very big RAM buffer, you can dump also scenes from the past to your disk. We are working with recorded images a lot and therefore use ROSBACs. And when recording datasets, you sometimes make not everything correct. You may either publish a wrong image encoding, or you may decide to rename your frame IDs, or you may want to add offline computed sensor data like disparity images later, or you finish a labeling process and want to include the ground truth data inside your bag. These are all real examples, and we especially like, in this case, the ROSBAC Python module, which works just great for modifying and rewriting bags. Other powerful tools and packages are, for example, the nodelets package. So we normally write only nodelets and small node wrappers that we are able to make use of zero copy, while also during creation of experimental software we can use them as nodes and not the whole graph crash. And for example, my whole traffic light recognition pipeline is realized as several nodelets. And we always try to use ROS standard messages or message packages that already exist, and this way get a high grade of exchangeability. I'm personally also a big fan of the image geometry package and use the 3D to 2D and 2D to 3D projections quite a lot. Also, we are big fans of TF as essential for our transformations. And over the time, we also set up detailed launch files, and especially like that you can nest launch files inside other launch files and can use arguments in this context as well. Also, the whole diagnostics idea is great, especially when you are working with a setup with dozens of nodes. So to wrap it all up, we think that ROS already includes the concepts to realize complex heterogeneous sensor setups. We like the capabilities of ROS for handling high data rates and cycle rates, and if your needs exceeds what ROS comes with, then just extend it. And that's it. Thank you very much for your attention, and I'm ready for questions.
All right, we'll take questions from the audience. There's one here.
For your extrinsic calibration, your node diagram showed a node called total ST. So are you using a total station to track and develop the extrinsic calibration from that?
That's right.
Great idea.
I simplified the slide a little bit, but we are using a total station, and we do an initially measurement of the car frame. So we measure the 4 wheels, and then we get the car frame, and then in the same run we calibrate all sensors.
Next question here, thank you.
So I just had a question regarding all your CAN ROS packages. So one of the hardest things that I encountered when just building any autonomous thing on my own using a CAN bus was the lack of availability of resources to do such a thing. So do you guys have any plans ever to open source such a thing?
Well, actually, the whole CAN bus messages is a big secret for the OEMs, and we don't have any plans to release it. You can anyway get the small subset, like for example with the ODB standard, Open Diagnostics bus, I think exactly, where you can get basic data, but I don't think you will be able, without signing an NDA with any big OEM, to get anything else. Next one.
Yeah, we've got time for one more. This one is first.
Sorry, do you have any plans to open source any other parts of that stack?
I would like to. The problem is that we are not allowed to participate with open source projects. So the only thing giving something back is do presentations like this one. You're welcome.
All right, we'll just take this one as well. That was a quick one.
You mentioned that the image calibration does not do sensor-to-car calibration, but you didn't describe how you do that in your talk.
What's the main part of your question?
The sensor-to-car calibration aspect, not just calibrating cameras, but calibrating sensors and their positions on the car.
Sorry, I not get it acoustically. The extrinsic calibration.
Yeah.
So you want to have more details, or what's the question?
Yeah, I want to know how you do it.
Okay, we have, for example, for cameras, we have a checkerboard. We have a reflector on the checkerboard that can be measured from the total station. We initially calibrated the car, so we know the transformation from the total station to the car reference system, and we can measure the checkerboard. So we have the 3D distance information, and we can find the checkerboard inside the image using the checkerboard detection, so we can solve the problem.
Okay, thank you.
Fantastic. Let's thank Andreas once more.